Okay, good afternoon and welcome to Q&A Friday. So we are going to do I've got 1 hour, I've got another meeting at exactly 1 o'clock Eastern. So I've got 1 hour and 3 minutes to get through some questions and provide some answers. As you all know, the reason I go live and I don't record is because I don't have time because got a lot of other things to do. So I want to answer these questions and I want to give them their due. I want to give them their due attention. So we are live on 1, 2, 3, 4, 5 platforms right now. So if you're watching, thank you for joining. Please use the chat if you have any other questions. I am going to walk through my channel questions and answers. So I'm going to go back a little bit, maybe a little over a month ago. I'm going to see how far I want to go back here and take a look at some questions because I've answered some of these already. Okay, so I'm going to start with a question on AFCIs from Santiago Arias Guzman. Hopefully I said that right. He says, Mr. Dimitrovich, I have a question. Does the AFCI safety webpage you showed at minute 53, this was the session on arc fault circuit interrupters and fire protection with David Smith and myself, showing 53 minutes, works also for people outside of the United States. Could someone get a callback or email solving questions in Spanish or another language? Thanks in advance for such awesome content. So Santiago, I would say give it a try. It's the internet. So put your question in. If you have a question, go out there to the afcisafety.org. If anybody is not sure what he's talking about, if you go to and follow me here, www.afcisafety.org, this is the website, and you can go in here and homeowners guide, tips, unwanted tripping report. So you can click on unwanted tripping report and fill out all of your information. Fill out your, it says city and state, and it doesn't have a international perspective to this. But you know what? I would say force the issue. I'm all about breaking some rules here. So pick a state. If you have to pick a state, it says it's required. You can, I don't know, pick the first one. Pick Alabama. We'll just blame it on Alabama. Pick Alabama, put your information in, and there is, I believe, a note right here. Describe the tripping incident. You can state that you're in a different country if you have a question about AFCIs or whatnot. And from a NEMA perspective, we have Spanish-speaking individuals who can translate things. And you know what I've learned? Google Translate will help us do that as well. So yes, please use it, Santiago. Be the first and make it happen. And what I plan to do is I plan to take this video and I'm going to link it to these questions. So the first one is Santiago Arias Guzman, and that was 1 month ago on arc fault circuit interrupters and fire protection. Thanks for the question. All right, so let's take a scroll up. Good morning. This month also going to be a great opportunity to have huge improvement on our knowledge about energy. Yes, Felix Sandoval, we had an energy month last month, so that's the way it goes. Okay, let's take a look at the next question. Matthew Hermanson says, like requiring GFCI protection for condensing. I'm going to move this over here so at least I'm looking that direction. Like requiring GFCI protection for condensing units so that we can't use variable frequency flow systems when a wire type equipment grounding conductor would have made that Chicago installation even safer. All right, so what Matthew is speaking to, this was the energy codes discussion, which this topic, I'm not sure how it relates to that video, but I know what he's talking about. If you think about 210.8F in the 2020 version of the National Electrical Code. Again, 2020 version of the NEC. You got to grab your code book. 210.8F is a requirement for GFCI protection on outdoor outlets. And what drove that requirement was a death associated with a child who touched an HVAC unit. If you do your research and your homework with the Consumer Product Safety Commission and search their database, you'll find that there are a lot of other deaths associated with HVAC systems, either touching those units or working on those units. You know, troubleshooting HVAC. Anytime you're troubleshooting, you can't establish an electrically safe work condition because you need power to do some testing, as you're, for obvious reasons. So at least it's obvious to me. The thought process here to remember is that, Matthew, simply grounding something does not mean you will not be electrocuted. Okay, and why do I say that? Grounding and bonding helps trip the overcurrent protective device. Yes, for when you have short circuit type of events. But a very high impedance fault internal to that unit does not mean you're going to trip the thermomagnetic circuit breaker that's protecting that unit just because you have grounding. So, and even if it's grounded and it is a low-level fault current, if you're touching that unit, remember ground fault currents will take not just the lowest impedance path. Ground fault currents will take all paths back to the source. So you could still be in parallel with the equipment grounding conductor and still receive more than 4 to 6 milliamps for an extended period of time. Again, depending upon the level of fault, etc. You can't, ground fault circuit interrupter protection is not there for when everything goes right. Ground fault circuit interrupter protection is there for when things go wrong. I would agree that pulling a solid bare equipment grounding conductor is probably more reliable. But if I was a raceway manufacturer, if I manufactured those flex or whatnot that was used, I would say, hey, that's just as reliable. And I could accidentally pull out that equipment grounding conductor, just like I could accidentally destroy my ground fault current path when I damage my raceway. So in any case, it's there because it's there. What raised the attention to 210 for the requirement of 210.8F was a death. Research shows there are other deaths associated with that. And we could have a debate on whether or not we need to, reduce the likelihood of shock. Be more than happy to have that debate, but probably not online right now. So that's sort of the story behind that, Matthew. Thanks for your comment, though. I really appreciate the feedback, and I know everybody has an opinion on this one. So there's people on every side of the coin on this one, and there's probably more than two sides to that coin. Okay, reminder to hit the like button. So Robert from Omaha says a reminder to hit the like button, and you know what I did, Robert? Subscribe. I got a little button now that says, hey, don't forget to subscribe to my YouTube channel. So, Robert, I'm not good at telling people that, but I'm telling you now, don't forget to subscribe. All right. So thanks for bringing that up, Mr. Robert from Omaha. Yes, TSDN. If you see that acronym, TSDN, those are the individuals that were following and watching videos last year during our little COVID crisis and everybody was in the house. I called this the Technical Social Distancing Network. So I still like that ring to it. Anyway, at 37, if fault current is less than 150 amps, then would these circuit breakers be coordinating in case current is low because of earth fault? So Navneet Garg, and what he's speaking to is the selective coordination session I did. It was the selective coordination and overcurrent protective device basics video. I'll try to put a link to that video here, over here. So in that video, I showed two trip curves of an upstream and a downstream breaker, and I had a fault current that was low, that was not into the instantaneous pickup region of the upstream circuit breaker. So the key thing to remember on selective coordination is you have to do an evaluation of overcurrent protective devices with regard to fault current that will pass through those two devices. So if the fault current is not high enough to be in the instantaneous region of the upstream circuit breaker, then indeed you are your application is perfectly fine with regard to selectivity. And I am going to attempt to do something here. This is going to be a trial, and I know I'm eating up precious time, but I'm going to do that anyway because that's what I do. We're leveraging new technology, so I'm trying some things that are different. I don't know if I'll be able to get this done, but we're going to try it. Okay, so I am going to do this. Delete. And I'm going to set my background color to black. Close that. And then I am going to do this. Studio mode, I think it was scene 7, scene 6. Yep, scene 7, scene 6. That was it. Close this up. All right, so what I'm going to what I want to do is I want to just give you that what we're talking about. So if you think about the time current characteristic curve, I have a TCC. I've got time up the axis, and I have amps across the bottom. If I have a downstream circuit breaker that looks like this, and I have an upstream circuit breaker, and I'll make this an electronic trip unit that looks like that. What we know from these two curves is that if I have a fault current that is anywhere greater than this point, so if my fault current is greater than, and that green line shows you the instantaneous pickup of the upstream circuit breaker. If my fault currents are greater than that pickup point, then I know that I can't rely on telling you whether or not the downstream breaker will clear and the upstream breaker will keep its contacts closed based upon the time current characteristic curves. I would have to go back to additional information from the manufacturer, and what we use are the selective coordination tables where we actually test pairs of circuit breakers. We have an upstream breaker and we have a downstream breaker, and we test those together. We push current through both of those, and we know at what point do they both open, and then we tell you that number, and we say, okay, as long as your fault current that passes through, I don't care if it's a ground fault current, I don't care if it's a three-phase bolted fault current, I don't care if it's an arcing current, if current passes through those two breakers persistent enough at a high enough, then that green line, then or that in the tables, based upon the numbers in the tables, then I know they're both going to open. So the green line for that might be somewhere in here, which is based on the tables. And this is based upon the TCC. So one number which will be higher than what you see on the curves is going to help you understand when you will have enough fault current that will open both circuit breakers, and that's called a selective coordination study. And we do that in SKM, EDSA, Easy Power, whatever application that you're in, and that's how we roll. So So that's what his question was. If fault current is less than 150 amps, so in that case, I'm assuming here that 150 amps was this line right here. That was the 150 amps. And if the fault current is less than that number, then yes, and it could be like I say, if you want to do an evaluation for ground fault currents and say what happens on a ground fault current, which one will open? The ground fault currents might be less. They could be more, but they might be less. You could say, what about an arc flash, an arcing current? They could be less. And you just, plot your available fault current and look at that fault current in regard to the time current characteristic over time current characteristic curves. So that's basically what's going on there. And so, my answer to you, Navneet, is yes. If it's less than that instantaneous, then yes, you are selectively coordinated, or you're coordinated for that value of current. If it's not the three-phase bolted fault current value, you can't say I selectively coordinate, because that means all currents, all times, and all the ways up to the three-phase bolted fault current. If you pick another value of current, then what you're doing is you're accepting some risk with regard to whether or not the current will be greater than whatever it is that you pick, right? And that might be perfectly fine for your application. So hopefully that helps you, Navneet Garg, in answering your question. William Snyder, wow, I didn't realize there were so many top dogs in the electrical industry here on Tech Tuesday. All right, man. Anybody who's attending these sessions, top dogs in my book. Okay, how about Navneet says, had another question. At 10205, and this is in the interconnected systems, what happens if fault currents in distributed resource? Would the MID, the mid, so we're in 705, so if this was interconnected systems, this is going to be up there in Article 705, the interconnected electric power production sources. And remember, this is the one that we were talking about, interconnecting, working in parallel with the utilities. So Navneet says, what happens if fault currents in distributed resource? Would the MID detect it? And if the mid detects it and isolates, then we might not have any power for critical loads. Shed some light, or it would open breaker B2. So here's the thing. The MID device, that is the microgrid interconnect device, and that is defined in Article 705 as a device that enables a microgrid system to separate from and reconnect to, operate in parallel with a primary power source. Okay. When would I find a mid? If I'm going to operate in parallel with the utility. So that would be like a photovoltaic systems and things of that nature. And when you talk about a critical load, Navneet, it depends on your application, what you mean by a critical load. If you're talking about, say, an Article 700 load for a life safety system, if you go to Article 700, Article 700 gets into talking about your power sources. Temporary source of power for maintenance and repair, transfer equipment. I'm just trying to, there's a capacity and rating. The emergency sequencing shall be suitable. I'm looking for where in here. Emergency sources, assign. No, that's sign. It's sources of power, part 3. I knew there was something there. So part 3 goes over all of the requirements with regard to sources of power. So when you talk about if the mid detects a fault current, which, it's not going to contribute, it's going to cut off. It's basically going to shut down if you have a fault and you're not going to feed that fault. So your comment about you might not have power for critical loads. If you're talking about Article 700 type of loads, Article 700 has Part 3, sources of power. And I would question whether or not your source of power actually would suffice to meet the application because of the reliability concerns that you would have for things like solar photovoltaic systems. We have recently been recognizing in the National Electrical Code and in NFPA 110 and 111 the permissions for those I can never remember the name of that. Anyway, energy storage systems that are certain types of energy storage systems that that would be permitted to be used in those applications. So you got to check out 517, NFPA 99, check out NFPA 110 and 111 for what would be considered okay. But I would argue that if you have a PV system that's operating in parallel with the utility, you're not going to be using that for an emergency critical loads because of Article 700, 701, 708, 517, NFPA 99, and other restrictions that says what you can and can't use. So hopefully that helps clarify that for you, Navneet. Thank you for the question. Earl Clemens on the 15-minute Tech Talk with regard to the 30 kVA transformer. Now, this was an older video I did in August 4th of 2020. This was back last year. Can you hook up backwards? Can you hook up backwards for a step up transformer? So to step up the voltage. And you can. Now, remember that you can backfeed through a transformer, but you have to follow the rules if you're going to do that. And the rules around, and I'm not sure if I'm going to be able to find it, but you're going to want to check Article 450 for backfeeding, and what it tells you is that a transformer is somewhere here in Article 450. So Earl Clemens, somewhere in Article 450, you're going to be looking for, when you backfeed a transformer, it's going to tell you that it has to be listed for that, because here's the issues that you have. When you start modifying a transformer for an application that it's not intended for, you start to encroach on, are you violating the UL listing? Are you going to void the manufacturer's warranties and things of that nature? You have to think about, is it a delta Y ground? And if you backfeed, are you going Y ground to delta? If you want a grounded secondary, then you're going to need to handle that and make sure that you wire it and et cetera correctly. And bonding is very important. Those will come, all of that information will be a part of the installation instructions that you get from the manufacturer. So make sure it's listed for that application. There is permission for that. You have to think about how you protect it. You may have to size your overcurrent protected devices a little differently. But yes, you can backfeed through a transformer. I would not use my information in that video for a transformer that's fed in a backfed situation. I would suggest that you probably should think the inrush currents are going to be a little different. So always talk to the manufacturer. So hopefully, Earl, that helps you. Thanks for the question. So I really appreciate that. All right, so Navneet Garg, I have a question. Suppose we have a grid supply with 500 MVA short circuit, assume an infinite bus. So it's when you say a grid supply, you're connecting to a secondary network. You have very high fault current. If I connect an isolation transformer of a small kVA of equal turn ratio from the grid, so now what they're explaining is they have a grid with a very high fault current, and they're going to put an isolation transformer 1-to-1. And let's just say for giggles, it's a 208 volts. So it's a 208 volt system. So you have a 208 volt transformer, and they say consider a 4,000 kVA transformer. And I put a 4,000 kVA transformer, meaning it's a 1-to-1, 208 to 208. Now I calculate transformer secondary current and then the fault current by dividing it by the transformer's impedance. Yes, so far you're good. How does isolation transformer is able to reduce fault current? Wait a second. Okay, well, I'm going to read this entirely. I have a question. Suppose we have grid supply with 500 MVA, assume an infinite bus. Now, if I connect a isolation transformer of small kVA of equal turns ratio from the grid, consider a 4000 kVA transformer. Now I calculate transformer secondary current and then fault current by dividing it by the transformer impedance. So if a fault occurs on the transformer primary terminal, how much higher fault current should flow than if a fault occurs on the secondary terminal? How does isolation transformer is able to reduce fault current? Does transformer saturate? I know transformer has impedance, but would that impedance be able to limit fault current that much? All right, so remember, when you're putting a one-to-one transformer, hey, Nihad, YouTube streaming is not live. Oh my gosh, it's not live? Hold on. Hold on, I'm glad you said something, Nihad. That's not good. Let me go to my, oh my goodness, I'm not sure why it's not live. Live? Oh, I know why. I did not put unlisted public publish. All right, so now I should be live. You know what I did not do, Nihad? And my mistake. This is you know what this is? This is being green. I did not, and I'm going to delete this other one. No, I'm not going to delete it. I did not. I'm just going to make sure that I am live on YouTube. My goodness. Your channel. There it is. So I think I'm live now. My goodness. Nihad, go check it out. And thank you for doing that. Let me get a shareable link. I got to go and just, well, I'm already live on Facebook. So anyway, all right. So this is what happens when you go live. I forgot to put the link to my live event. Dadgummit. Thanks you, Nihad. Thank you very much. I screwed that one up. So anyhow, let me go back to my questions here. Goodness gracious. Playlist. Comments. Let me go back to comments. All right. Well, this is for those of you. That worked, man. I made it. You know what, Ryan? I started this and I forgot to put the stream link from my scheduled event, and I just went live, and for some reason the default was private. I think it was because I was testing this ATEM Mini Pro, and I put it on private because I wanted to just make sure it worked. So you guys are going to have to go back and watch the first 25 minutes later. All right, so I was in the middle of answering the one-to-one transformer, and the question was on my transformer applications and protection, and it was about assuming an infinite bus, about 500 MVA on the primary, connecting straight to the grid. How does a transformer limit fault current? And I would suggest, Navneet, that what you have to do to understand what a transformer does for fault reduction, we have to understand, and you made the statement, you said you know that a transformer has impedance, but would that impedance be able to limit the fault current? And my answer to that would be yes. It has an impedance, and we know what the impedance is, and we know that the impedance of that transformer, if you look at my infinite bus video, I will try to put a link to that up above. The infinite bus video that I did goes through the calculation, because remember, an infinite bus, to understand an infinite bus, you have to understand the impedance diagram. And the fact that my source, that 5,000 MVA short circuit available fault current from the utility that you're talking about, that's on the line side of a 1-to-1 transformer, is a very small impedance. So if I draw we're going to try this again. And while I'm doing this, everybody, remember to subscribe to my YouTube channel, because I'm starting to travel now, and I would say that what you want to do is make sure that my consistency might be a little different than what it usually is. So just be mindful of that. All right, so I'm going to do this. New slide. Oh, I'm not going to do a new slide. I'm just going to delete all of this. All of this stuff. Draw. Select. Let me delete everything here. Okay, delete. And I'll show you what I'm doing so you don't feel lost and alone and afraid. Delete. Okay, so what I'm going to do now is, we were talking about the impedance diagram. So if I have a transformer, and it looks something like this, right? And let's say that it's feeding a panel, and I'm not going to draw the circuit breaker. And there's a utility up above. How I would model this is an impedance for the utility, an impedance for the transformer, an impedance for the secondary conductor. Okay, so this is the utility. Oh man, I don't have my pen, so I'm using my big fat finger. That's my utility. This is my transformer. And this is my conductor. And what this all comes down to is your basic short circuit calculation, your ohms, your Kirchhoff's laws, your Ohm's law of V is equal to IR, right? So how do I do this? I just, I draw a voltage, and these are all of my conductors. This utility impedance is really small as compared to the transformer impedance. So it's about the impedance of the transformer. That large impedance of the transformer in this circuit is what governs the available fault current. Regardless of that utility, it's so small, it's almost insignificant. And I have a video that I go through the calculations of infinite bus, and I draw this. And in fact, I did a session on per unit calculating fault currents, and we went through all the math associated with calculating fault currents. And my thought process is, if you understand how to calculate short circuit currents, how to convert every component that you need to convert into an impedance within a power system, you will understand where your fault contributions come from and why the numbers are the way they are, right? So watch those two videos. I think you might get some value out of those. I'm going to leave this live over here so I can go back and get it later if I need it. But trying some new technologies. Okay, so hopefully, Navneet, that helps you understand. It is about impedance, and if you want to understand how do they come up with the percent impedances through the short circuit and open circuit testing that's done on transformers, I don't have a video on that. There's a lot of material in textbooks. I would reference IEEE IEEE color books. I'm not sure which one. What I might do is I might get my transformer guys and talk about how we determine percent impedance. There's a concept. I'll work with my transformer people and we will get a live session put together on how a manufacturer establishes the percent impedance of a transformer. So stay tuned for that one, Navneet. Hopefully you can tune into that when we do that. All right. Nina Price, thank you. Appreciate you too. And Leslie Sun, very nice tech talk. Thank you very much, Leslie. I really appreciate everybody's feedback. So, thanks. Anytime. All right. So another question. JW. And JW just hopped on. We had some good discussions. I think it was yesterday, Tech Thursday. And JW says that he asks a lot of questions, and that is perfectly fine because that's how we learn. So JW said 3 days ago, the new definitions policy in Article 100, perhaps they should then have a practice of underlining the terms that have definitions. There's some that we all know, but some for special conditions, special occupancies, or special equipment that many may not know if they read a given article. Someone who doesn't work with a specific type of installation will normally spend some time in the article that covers that topic if they are planning to do work that covers it. This includes that they would spend some time looking at the special definitions for that article. Now, it becomes more difficult as they would need to re-review all of Article 100 to pick out certain definitions that may only be applicable to that topic. Wow, JW, I like your thought process. Moving the definitions to Article 100 is a controversial discussion. There are individuals on both sides of the fence there. Some people are saying do not move the definitions, keep the definitions in the .2. And if you're not sure what we're talking about, the 2023 code cycle is looking at moving all of the definitions. And if you're familiar with the code, you know that .2, hey, David Engelhardt in the house. I'm going to answer your questions too, David. I've got a hard stop at 1 o'clock, so I'm going to hit yours as well. But JW had a good point that in the 2023 cycle, they're looking at moving all the definitions, say, out of the .2s. And if you look through the code, like I just opened up this article 626, electrified truck parking spaces. 626.2 says definitions. The following definitions shall apply only within this article. And then there's a list of definitions. There's electrified truck parking space. There's overhead gantry, separate power supply cable assemblies. They define a truck. A truck is a motor vehicle designed for the transportation of goods, services, and equipment. So apparently, if you do that in your car, like you're a pizza delivery person, you're not a truck. Okay? So, or if you do, a motor vehicle designed for the transportation of goods, services, and equipment. So if you do pizza delivery and your vehicle has been specially equipped, you're not a car, you're a truck. Anyway, I diverge. What they're doing is they're moving all these definitions in the 2023 cycle to Article 100, and they're uncovering a lot of issues associated with one term being defined more than once, and then they're questioning, why don't we just combine those into one definition and get one definition that covers all of those situations? So, JW, you do have a good point, though, that it would be really cool if any of the defined terms in the National Electrical Code, if they're in, like, for example, we defined a ground fault circuit interrupter. Anywhere where that is used, it would be really cool to underline. Oh, there we go. So Ryan says the ICC books, the building code and the residential code, italicized defined terms, but I think that would be a mistake in the NEC. Consider the misuse of identified, for example. It is usually used incorrectly. Well, I don't know. I think it would be Ryan. I think JW. I look forward to your public comment. I think there might be something there. I don't know, but that would be an interesting thing. So I like where your head's at, and you know I know what side of the roof you're on. Thanks for the comment, or thanks for the question, or the comment. I'm not sure. I think it was a comment. All right, Blue Sea. Thanks, very useful. Glad it was helpful. Excellent. All right, and my plan on this is to, on these questions, I will respond with a link to this video so that those who ask those questions, because like I said in the very beginning, which some people on YouTube weren't here, how to design a substation. That could be a very long live session. All right, so there aren't many people that are good with NEC rules for medium voltage. A lot of medium voltage people know only utility things. And this comment was on the medium voltage and the NEC video, NEC 2023 video that we did a while back. And I think I had Larry Air on for that one. And what JW is pointing out is that, and I would tend to agree that I think a lot of people assume that when it's medium voltage, that it's not covered by the National Electrical Code because it's owned by the utility. But there are a lot of privately owned medium voltage applications, and I think that is growing. And I know this is another controversial topic. There are those that say the code is adequate. The code has everything you need. There are other people that'll say no. There are a lot of holes in the NEC, and then those who say that you shouldn't change anything or do anything with medium voltage changes that are coming down the pike and in the code change will say, well, you know, make your public comments because they're not coming in. So in any case, this is the 2023 code cycle is looking at changing or rearranging the National Electrical Code with regard to medium voltage. And it is another one of those controversial topics, almost as hotly debated as the moving of Article 100. Oh, Chris Folan, how do you ask questions for Q&A Friday? Just send me an email or comment one of my videos. So this will be posted. If you just simply put your comments and your questions in, if I don't get it to them now, I will get to them next Friday. So what I'm going to try to do is do a Q&A on Friday at noon, as long as I'm not traveling. And I'm thinking, based upon my schedules that I'm looking at coming up and the events that are occurring, in-person events, I sort of like drive on Mondays or Sundays too. But Fridays seems to be, I don't know, looking good moving forward. But in any case, if you have questions, send me an email. What you can do here is I will, let me just do a scroll. I'm going to modify this to say email questions, Thomas A. Domitrovich at Eaton.com. I'm gonna see what that looks like. So if you look down below here scrolling, you'll see my email address will eventually come across there. Send me an email with your question and I will get to those. And I know David Engelhardt has sent me some questions as well, or at least one. And I had another one too from another inspector, which we'll talk about that one. And it's 12:40. So what I am going to do, while I'm getting ready here and answer another one, I am going to open up my email that I forwarded. All right, so JW had another one. Control panel wiring in a substation. I will, you know what? I will do one of those, I'll just say Zondi. I will focus that. So I will try to focus on some control power wiring in a substation. Okay, here's another question from JW. There's still an issue may exist. Okay, so there are many people. There's still an issue that may exist even with different articles for medium voltage, high voltage, and low voltage. For instance, low voltage wiring and equipment in large, high voltage, customer-owned substations, it still could be a problem that the people in the low voltage focused committees will be making low voltage rules without consideration of low voltage in a high voltage application. And I think that's Zondi's comment too. So JW, what I'm having a hard, I've got to look into that. Because if I would think about a medium voltage application and low voltage wiring in and around a medium voltage application, if I'm in an enclosure, if I'm in a piece of equipment that's listed or tested to an IEEE standard, they address the mixing of the low voltage and the medium voltage. That's all handled by the manufacturer. If you are doing something outside of the equipment, connecting your medium voltage conductors, I'm not sure exactly what I would do different than what's already covered in chapters 1 through 4. And that's not, I haven't dug into it. I may not completely understand your application and where your concern is with regard to chapters 1 through 4 not being adequate for the low voltage wiring in and around medium voltage equipment. Be mindful, though, that in my mind, I'm thinking you're buying either a listed medium voltage assembly or an assembly that hasn't been modified by anybody other than the manufacturer when it was shipped, right? I just think that I'm just having a hard time understanding where the inadequacies would be. I'd love to hear your thoughts in that regard. If you have some specific examples, that would be great. So if you could bring those specific examples to the table, I would appreciate that. And now JW had another comment on the 90 degree and 105 degree things too. Low voltage breakers have thermal heating units that can actually be heated to nuisance trip due to heat of the conductors. Medium voltage equipment using things like current transformers isn't subject to the same heat from the conductors. All right. That's a good point. And when you get into medium voltage applications, so I think what you're talking about are the 75 degrees C, the 80% versus 100% rated with regard to 100% of the ampacity, not having to do the 1.25 multiplier. You are right. When you land conductors, you're still landing them on a circuit breaker, but there's no thermal element. You're basically tripping that breaker based upon a relay that is monitoring CTs and PTs and deciding when to tell the switch, so to speak, to open. So I know we have that we don't have the same temperature issues going on in that regard. So hopefully, I'm thinking that I'm hoping that I'm tending to agree with you. I think what you're saying is adding more clarity to the discussion around medium voltage, and using, say, not doing the 1.25 for your continuous loads more than 3 hours. All right, so I want to go to Mr. David Englehart's question, and I have to find it. I've got David Englehart. So let me search Engelha, and I believe Englehart. I'm not seeing it, so I think it's still on my other email. So David, what David's comment. David was commenting on 24087, and it's my PC ran into a problem and needs to restart. All right, so I'm gonna let that do its thing, and I'm gonna go off of memory, David. I don't know, maybe I can find your email. So David's comment was around 24087 in the National Electrical Code, and the requirement in 24087. Thanks, David. I see your note. 24087 is, and his question was, how do you catch it, right? So how do you, Engel, David Englehart. All right, here we go. Still trying to wrap my head around arc energy reduction. All right. What is it appropriate to look for it during the plan review stage, at the inspection, or both? He has plans that have that the applicable overcurrent protective devices appear to indicate LSI, which believably translates into long time, short time, and instantaneous. And for certain application situations, would include G at the end, which would mean ground fault, which would meet your 230/95 requirements. Does the instantaneous indication provide what I need, LSI in its entirety, or do I need more information? Being in the 17 code, so he's in the 17 code, it appears that once we go into the 20 code, a performance test will be required as GFPE does. Wouldn't this be inherently included by the manufacturer, or does it need to be requested by the purchaser? I hope I'm not the only one with this fogginess, and I don't believe you are, David, and that's why I think it's important, because I've gotten the same question numerous times from different people. The last one before you was from a gentleman in Ohio, and we actually went through his application, and we looked at the drawings, and we looked at what was provided by the consulting engineer. Now, 24087 has a couple requirements, and I'm just going to call up my 24087 dialogue, and I do have a hard stop in less than 10 minutes, or at 1 o'clock, or yeah, 1 o'clock. NFPA 70. I'm going to grab the 2020 code, my presentation, and presentation 24087. Arc energy reduction. All right. And I'm going to go to here. Okay. So now, and before I do, yeah. Okay. So arc energy reduction. I'm going to go to the language. So here's what it says in the 2020 code. Where the highest continuous current trip setting for which the actual overcurrent device installed on the circuit breaker is rated or can be adjusted is 1200 amps or higher. Very similar to ground fault protection of equipment. Okay, so GFPE is the 1000 amps. So if you go to 230, I went the wrong way, 230/95, I believe it is. If I have my numbers correctly, ground fault protection of equipment, it says ground fault protection more than 150 volts, but not exceeding 1000 volts face to face for each service disconnect rated 1000 amps or more. Blah, blah, blah. The rating of the service disconnect shall be considered to be the rating of the largest fuse that can be installed or the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted. So that's where we got that language from was from 230/95 for ground fault protection of equipment. So it's easy to recognize when you are into 24087. So to your first question of should you catch it in plan review, should be looking at it in the field. Plan review is your first place. Plan review is critical, in my opinion, because if you don't catch it in plan review, and then you wait to go out in the field and you look and you see a 1200 amp circuit breaker, and now you're going to say, okay, it's 1200 amp circuit breaker. Now I have to get into whether or not it has, what are the technologies, right? In 24087, when I get to the method to reduce clearing time and the documentation, you're too late, in my opinion. The information is in the equipment shop drawings that do not get submitted for review, and will update his specs for the Eaton gear to include this information. Absolutely. You want that information. So that might not still be enough. If it's coming from Eaton, the manufacturer, yes, Chris Farland, if it's a 1200 amp frame breaker and has a 1000 amp plug, okay, so, oh, this is good stuff, man. Remember to, okay, look at what this says. And I'm going to put you back to 240.4. Is it 240.4? No, 240.6 maybe. Yes, 240.6. Don't make this mistake, even on plan review or in the field. 240.6, remember, this says where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated. And where do we go to get the rating? We go to 240.6. Don't make this mistake and think that because I have an adjustable trip circuit breaker and I adjust it to 1,000 amps, and it's a 1,200 amp frame breaker adjusted down to 1,000 amps, and I have a door that the rating of that breaker is now 1,000 amps, and I don't need to do 240/87. And the reason you can't do that is because of the next few words in this paragraph. It says, in a circuit breaker is rated or can be adjusted is 1,200 amps or higher. Same thing goes for 1,000 amps on ground fault protection of equipment. If I have a 1,000 amp frame, well, you can't buy a 1,000 amp frame. If I have a 1,200 amp frame and I adjust it down to 800 amps, and I put the little lockable door on it, or based upon the latest version of the code, I can have password protected in the 2020 code. That does not mean that you don't have to have GFPE. That does not mean you don't have to have an arc reduction technology, because you can still adjust it to 1,200 amps. That's the key. If you can adjust that circuit breaker to 1,200 amps, then you have to get into 240.87. If you have a plug in there that is a 1,000 amp plug and it cannot be adjusted greater than 1,200 amps, you have a good argument with the inspector to say, look, I cannot adjust that to greater than 1,200, to greater than 1,000 amps. Now, they may say, well, you can take that plug out and put a 1,200 amp plug in, and they've got a valid point, but that, again, you're on that area where you're going to be arguing with an inspector. And remember, arguing with an inspector is like wrestling with a pig in mud, because soon enough, you'll understand that the pig enjoys it, right? So they love to argue, and that's perfectly fine because their butt's on the line with the inspection. And you've got to respect that. So you've got to have this clear up front, but I don't know that anybody makes a 1,000 amp sensor or a 1,000 amp plug. They'll have a 1,200 amp and they'll have an 800 amp. You're not going to have that 1,000 amp plug. If you have a 1,200 amp breaker, you're into 240/87. So hopefully that, and you catch that on plan review. You get that when you're looking at the plans, you're looking at the drawings. Make sure you get that information. So you should be able to identify exactly every place in that drawing where you have a breaker that is 1,200 amps or larger, or can be adjusted to 1,200 amps or larger, so that you know where you're going to have to review the requirements of 240/87. That's the first point of entry for circuit breakers is 240/87 is when you can adjust it up to 1,200 amps. Now, and catch that in plan review. Now, the 2020 code added another level of detail. You have to demonstrate, you have to first show on paper in the documentation. Remember, in A, the documentation tells us that we have to, here's a good example. There's a 1,200 amp frame that can be adjusted up to 1,200 amps. That is going to need it, but the 800 amp frame will not. Excellent, James. Let's go to documentation. What does documentation say? It says that documentation shall also be provided to demonstrate that the method chosen to reduce clearing time is set to operate at a value below the available arcing current. Okay, so that is the added meat on the table that the 2020 code brings to the table. You need to show that someone has to calculate your arcing current. Now, it doesn't give you any much more guidance than that. It doesn't tell you to use the minimum arcing current, the maximum arcing current, an average arcing current. It doesn't tell you to use 1584, IEEE 1584 to calculate arcing current. Someone is going to have to provide that information for you. And I'm just looking. It doesn't even say that it has to be a qualified individual. Arc energy reduction, documentation. Yeah, it doesn't even say in here that it has to be it says documentation shall be available to those authorized to design, install, operate, or inspect the installation. Documentation shall be provided to demonstrate that the method chosen to reduce the clearing time is operating below the available arcing current. So like on this one here, I've got the arcing current has to be in the instantaneous region, which has to be high enough over here to actually get into that instantaneous region. So somebody should show you a trip curve like this and show you the arcing current, or tell you, here's what the pickup point is for that instantaneous, and here's the arcing current in this application is whatever, and look, it's greater than that pickup point. So that's what you're looking for. But there's nothing in here that says that it has to be a qualified individual. So anybody can do that. I would argue you'd probably want to look for their capabilities. But and then once you have said, okay, so would the arc flash label be with the arc reduction, before arc reduction, or both? I'll tell you what they do, Chris. In many cases, they will put both on there and state it like that. There's nothing in the code. There's nothing in 70E. There's nothing in IEEE 1584 that says that addresses that, how you do that. It's personal preference. If you want to provide both labels, then I would do that. And especially if it's an arc reduction maintenance switch, I would do that. I've seen some people say, yeah, there you go, Ryan. Ryan's got a public input in for 70E to do both. I would say that some people will say, here is the line side if the clearing time is based upon the upstream overcurrent device, and then here's the instant energy for when the main overcurrent protected device clearing time. So the challenge there is to understand from a labeling perspective what is required, and then what is practical. And then also, you want, as an engineer, you want to provide as much information, but sometimes too much information is not good either, because when you put a person into a position, my dad, I'll just tell you, when we would be driving somewhere, my dad had one eye, okay, and he would drive, and we would go down the road, and he would see a lot of signs that would say, go this way for this, go that way for this. And he had to do a lot of thinking to figure out, okay, what am I doing? And he's got one eye, right? So he's looking back and forth. And in some cases, he'd be like, I'm not sure which way to turn here. And he would just make a decision and go. When you give somebody too much information, you might be relying on them too much. So you want to make sure that you give that individual, reduce the likelihood of them making the wrong decision. I'll just leave it at that. And you don't want them to make a mistake and be underdressed for the event. I'd rather have somebody overdressed for an event. All right, it's 12:59. I've got a hard stop at 1 o'clock. Please submit any questions. My email address should be scrolling. I think it's after the join IAEI. Membership has its values. Email to, what the heck? Look at that. Email to, oh man, Thomas. I'm going to take out the join IAEI. Thomas A. Dimitrovich at Eaton.com. So send me an email or comment on this video, right? So comment on this video. It's 1 o'clock. Comment on this video. There's my email address, Thomas A. Dimitrovich at Eaton, EATON.com. Apparently it's too long for the thing. So Thomas A. Dimitrovich at Eaton.com. Look forward to your, I'm gonna have to get on this call. So thank you very much for watching. Thanks for what you do for electrical safety. Thanks for what you do for the electrical industry. Thanks, Ryan Kurdish, James Smith, Eric Smith, David Engelhardt. Hopefully I answered. Chris Folan, everybody out there. Thanks for tuning in. I'm signing off. And I got to get on this call. I'm 1 minute late. All right, everybody, take care. Stay safe.